Welcome to Lubrication Fundamentals, where we demystify lubrication for operations, plant, equipment, service, and fleet vehicle managers. In this segment, we're going to go over viscosity, one of the fundamental attributes of lubrication, and why it's important. First and foremost, let's define what viscosity is. Viscosity is a fluid's resistance to flow. We'll dive more into that in about a minute. Viscosity is responsible for the force that determines the thickness of the lubricating film. As you can see by the image of the journal bearing on the right, the stationary shaft is displaced by a large layer of lubricant, where the film thickness is proportional to the viscosity. It's also physically an important factor in the cooling effect or heat transfer properties of the sealing ability of an oil. At both ends of the spectrum, viscosity is important in starting engines or equipment in cold temperatures, and equally important in running equipment at high temperatures. There are two types of viscosities: kinematic and dynamic. Fundamentally, kinematic viscosity refers to a fluid's resistance to pour, and is measured in centistokes. Similarly, dynamic viscosity refers to a fluid's resistance to stir, and is measured in centipoise. Most of the time, when we see viscosity grades, they are referring to kinematic viscosity. Let's look at a familiar example: mayonnaise versus honey. If we try to pour mayonnaise and honey, which one will pour easier? The honey, right? So mayonnaise has a greater resistance to pour than honey, and therefore a higher kinematic viscosity. Now, if we try to stir mayonnaise and honey with a spoon, which one is easier? The mayonnaise. So honey has a greater resistance to stir than mayonnaise, and therefore a higher dynamic viscosity. Now we can begin to understand that dynamic viscosity is important in starting machinery, while kinematic viscosity is important when a machinery is already running. Viscosity is not constant. There are several factors that influence it. First, let's talk about pressure or load. The greater the load on the lubricant, it makes it harder to flow, and therefore raises the kinematic viscosity. Conversely, the lower the pressure or load on the lubricant, the easier the lubricant flows, and the lower the kinematic viscosity. As a rule of thumb, viscosity doubles with every 5,000 psi of pressure. Next, we have temperature. As the temperature of the lubricant increases, the easier the lubricant flows and the lower the kinematic viscosity. Conversely, as the temperature goes down, the greater the resistance to flow and the higher the kinematic viscosity. This helps explain why the wrong lubricant in a cold environment makes it difficult to start vehicles or machinery. Now that we understand the two types of viscosity and the factors that affect it, let's look at viscosity grades. Earlier, we mentioned that kinematic viscosity was measured in centistokes. That said, ISO, SAE, and other standard organizations have different grades of lubricants that refer to a range of viscosities at a specific temperature. Let's look at the example of a single grade lubricant. If we take a 100 grade lubricant, we can see on the chart on the right that this lubricant will measure approximately 100 centistokes at 40 degrees Celsius and 11 centistokes at 100 degrees Celsius. Now, let's look at multi-grade lubricants. These lubricants exhibit two different viscosity profiles depending on the temperature. They are popular in vehicles as you want a lower viscosity when starting than you could achieve with a single grade lubricant. For example, let's look at a SAE crankcase grade 10W30. You can see the 10W grade aligns with a viscosity of about 25 centistokes at 40 degrees Celsius, and the 30 grade aligns with a viscosity of about 10 centistokes at 100 degrees Celsius. You can see that at 40 degrees Celsius, if we were to use straight SAE 30, the resistance to flow would be almost 4 times that of the 5W grade. Both semi-synthetic and synthetic lubricants use viscosity improver additives to achieve the desired properties. There are a wide variety of viscosity improvers that will affect the viscosity profiles of the mineral or synthetic base lubricants differently. So, what can go wrong? First, if the wrong grade lubricant is used, or a wrong grade lubricant is used to top off a reservoir, the change in viscosity can lead to difficulty starting if it's too high, excessive heat if it's too low, and excessive wear and oxidation of the lubricated components. The second issue is that over time the viscosity improver added to base lubricants breaks down. This is a function of the operating environment and overall endurance of the viscosity improver additive. At a certain point, the viscosity of the lubricant will change, and you will encounter the same problems as having the wrong lubricant grade. To conclude, 1. Make sure you're using and topping off with the correct grade lubricant for your equipment and operating environment. Operating a logging conveyor in the tropics versus northern climates requires different viscosity profiles. 2. Monitor your oil in critical applications to ensure it is still at the required specifications. Most lubricant analysis labs can report the viscosity of your samples. 3. If your oil is relatively clean, for example with no soot, Thermalube can provide options for reducing changeover times, disposal, and environmental waste, and increasing lubricant life. Consider readditization to replenish the viscosity improver in otherwise good oil, or a customized application-specific formulation. For more information or to contact us with questions, please visit Thermalube at www.thermal-lube.com.